So now that we have these estimators, one of the things that we're interested in is the distribution of these estimators. Okay, so let me explain. Let's take this for example. Right? The IQ of the individual in society is normally distributed with a mean of 100 and standard deviation of 15. Okay, so this is from chapter 6. Right? So we can say, okay, it's normally distributed, and here it is the mu equals 100 and sigma equals 15. Okay, so let me just write this out clearly here. Okay, all right, so that is the population, and let's label the axis X. Okay, so if I pick somebody at random, what's the probability that the person has an IQ higher than 110? I can draw that. Okay, 110. Oh, whoops, sorry about that. That would be 100. Excuse me, 110 would be there. And again, I'm still looking at X. All right, these are the individual IQs, and what I'm interested in is the probability that the IQ will be greater than 110. In other words, what is that area? Okay, and I can calculate that. I can calculate that pretty easily, right? So because I know the sigma equals 15, I know the mean, and so I can get that. I can get that area. Okay, so let's use our app for this. So go to your probability distribution. We're gonna select normal distribution. Okay, and the mu here is 100. Sigma is 15, okay, and my X value is 110, okay, and I want the right tail, perfect, and there we go. All right, so that is 0.25, all right, 253. All right, let's round that up. All right, no problem. Now, consider this question. If I pick a random sample of 10 people, what's the probability that the sample mean is greater than 110? So that means n equals 10, right? So now I'm no longer looking at X, but I'm looking at X bar, right, with the sample mean. And what I'm interested in is, what's the probability that X bar is going to be greater than 110? Now, to answer this question, I need to know a couple things. One, what is the expected value of X bar? What is at the center of X? What is the value of the center of X bar? And I also need to know what is the standard deviation of X bar, right? What is that equal to? Okay, and also most importantly, I need to know what is the shape of X bar. Is X bar normally distributed, or is X bar shaped like this, or is X bar shaped like this, right? I don't know. I don't know what the shape is, and if I don't know, so I need 3 pieces of information in order for me to answer this question. Okay, I need the shape, I need the expected value, and I need the standard deviation. Once I have these, then I can go ahead and try to calculate what is the area to the right. So when we say sampling distribution, what we're talking about is the distribution of the sample statistic. Right? The estimators that we are using to provide estimate for the population parameter. Okay? And this is going to be evidently very important when we get to chapter 9 about hypothesis testing. But for now, just focus on the fact that that any estimator is a random variable. Why is it? How do you know if it's a random variable? Well, because if you're taking the sample average, every time you go out and collected a new sample, you're going to get a different number, right? So, so hopefully use that to understand that it is random, because you won't know what the sample average is until you actually collect it. So there is a distribution there, right, that we want to understand. Okay, so first thing we want to know is the shape of the distribution. Okay, so fact number 1. Okay, if the original population is normal, or is normally distributed, then X bar is normal. Right? So if the normal, if you have some information, or if you make the assumption that the original population is normally distributed, then X bar will be normally distributed. Now, if you don't have that assumption, then we will have to use the second one. So fact number 2. If the sample size is large enough, Okay, and what is large enough? Large enough just means, let's say n greater than or equal to 30. Okay, now why 30? It's a safe number. Okay, so without getting too deep into convergence of distribution, just know that we have a large enough sample size, and if the sample size is large enough, then x bar will be approximately normal. Okay, and if we have either one of these, fact 1 or fact 2, we don't need both. We just need one. And once we establish this, then we are able to do this. We're able to draw a normal distribution for x bar. Okay, that is the goal of all this. Right? That is the goal here. Okay, that's how we establish the shape. The fact number 2, we call that the central limit theorem, or the CLT. Okay, and this is a very powerful theorem, because this means that we don't have to know anything about the original population, like the distribution of the original population. Right? And this is very useful because, in fact, we don't know most of the time, right? What is the distribution of income? We don't know. What is the distribution of height? We don't know. Right? We don't know the shape of any of these distributions. But central limit theorem says it doesn't matter. As long as we have a large enough sample size, then our sample mean, this is not x, but x bar. Okay, our sample mean will have approximately normal distribution. Okay, all right. Now the central limit theorem also lists out a couple other things. Let's go then one by one. All right. So 2, the expected value of the sample mean. Expected value of the sample mean. Okay, so the expected value of the sample mean, let's write that down, right, equals mu. So this gives us, so number 1 gives us the shape, right? Number 1 gives us the shape, and number 2 here gives us the center. This tells us that the center of the distribution must be at mu. Okay, and this is because x bar is an unbiased estimator for mu. Okay, that's why we can confidently say that the distribution is centered at the true population mean. Finally, finally the variability, right? We'd like to know what is the standard deviation of x bar. Okay, and so central limit theorem tells us that this equals sigma of x. Okay, so notice the subscript, right? This is the population standard deviation. Okay, divided by the square root of n. Okay, and that will give us the standard deviation of x bar. Okay, so from now on, right, because I don't want to confuse these two because I'm using the same symbol. So instead, right, we're going to call this, instead of writing this, we're going to say the standard error of x bar. Okay, that's going to call the standard error, but they're going to mean the same thing. Right? Standard error just means the standard deviation of x bar. So the standard error of x bar is sigma of x divided by the square root of n. And that will give you the standard deviation of this distribution. Okay, let's do one example here. Suppose the population has a mean of 25 and a standard deviation of 12. We take a sample of 42 people. What's the probability that the sample mean is greater than 27? Okay, let's piece everything we just learned together here. I have a population. I don't know what the distribution of the original population is, okay? But I do have a sample of 42 people. So my n equals 42, which is greater than 30. Okay, so that allows me, right, to draw like this normal distribution. I know that my sample mean will be normally distributed. Furthermore, x bar is unbiased. Therefore, I know that it will be centered at the mu. What is the mu? The mu is, they tell me here, the original population has a mu of 25. Okay, so I can write that over there. And the original population has a standard deviation of 12. So that tells me my standard error of x bar equals 12 over square root of 42. Okay, all right. And so now I want to know what is the probability that the sample mean will be greater than 27. That means if I go out and collect a sample, what are the chances that I will observe a sample larger than 27? And so now all I have all these pieces together, I can use the app to figure out what is the probability here. Okay, so first, let's go ahead and calculate the standard error. That is the standard deviation of x bar. So second, we'll go into normal distribution. Okay, and my average is 25. The standard deviation 1.85, and I'm looking at probability that is greater than 27. And there we go. That's it. Okay. All right. Okay. Let's go ahead and do example 3. Okay. If you like, pause the video and go ahead and try this on your own. Okay, so collecting the information. The household income of California is normally distributed. So that's a fact, right? That is a fact that's given to us in the problem with a mean of 65,000 and a standard deviation of 28,000. So right there, I can draw a graph so I can visualize it. The income is X, not X bar, just X. Okay, the center, the mu, equals 65,000. Okay, and the standard deviation equals 28,000. Okay, so that's what the problem gives me. This is the distribution of income, individual income, not the sample, not the sample mean. Okay, the probability that randomly selected in the household is below 35,000. Okay, so here's 65,000. Okay, so 35,000 is here. And so that's the area that I want. Okay, so again, label your axes will really help you keep things straight. I'm just looking at the individual here. So I want the probability that X is less than 35,000. Okay, so then now I can use my app here. The average is 65,000. The standard deviation is 28,000. Okay, and then X is 35. I want less than, and there we go. So that will be 0.142. Okay, all right. Now, what if I select 20 household? What's the probability that the average income is below 35,000? Okay, so first of all, my N is 20. Now that is less than 30, but the problem already assumed or giving me that the original population is normally distributed. Therefore, I can write this. Okay, so that's the important part. Always be mindful of what information allows me to draw this curve. So I know that the sample mean is going to be normally distributed. What is the center at? Because it's unbiased, it is centered at 65,000. And the standard error, the standard deviation of x bar, right, is going to be 28,000 divided by the square root of 20. Okay, so calculate that first, and let's go ahead and calculate. Right, go ahead and pause the video and go ahead and calculate that probability. Okay, so that's my standard error. Okay, so the only thing I need to change in my app here is the standard deviation. Notice the standard deviation is much smaller now. Okay. All right, and again here, that's not change, 35,000, and voila. What does that tell me? That tells me that the probability of x bar being less than 35,000, right, is approximately 0. Okay, all right. So why is it? What's the difference? What's the difference here? Well, remember, as the standard deviation of a normal distribution increases, right, then the observation or the data, right, or data is more concentrated in the middle. Okay, what that means is the original population, right, the original population might have a shape like this, but when we collect an n equals 20, right? X bar, right? Most of the data is much more peak in the middle, even though the middle is the same. The middle is in both cases, 65,000. 65,000. Okay. In other words, if you select individuals, then it is you can still find somebody that is below 35,000, has a household income of below 35. But if you select a group of 20 people, it is less likely that the average is below 35,000.